Good morning, everybody. Mr. Marek here. In this video, we're learning about magnetic fields. Now, we need to remember what a field means. And so magnets can exert forces on other magnets and some other objects, and those forces can be exerted over a distance. And that's why we refer to the magnetic field as a field force. Keyword in there is distance. Since it can be exerted over a distance, that makes it a field force. Now the rest of this is just a little bit of background, so don't feel like you necessarily need to write it down. But the effect of magnetism was first observed, as far as we know, as far back as 400 BC. People knew that iron would be attracted to certain rocks. These rocks were called lodestones, as far back as 400 BC. The compass was invented somewhere in 1100 AD, probably in China, and it was used for navigation. People could figure out which way north was by using a compass. And a compass is just a tiny little magnet that's kind of free to swivel around. So it'll line itself up with the Earth's magnetic field. But it wasn't until about 1820 that we understood the link between these magnetic forces, which really didn't have much use until then, other than the compass until then, and electricity. So electrical charges and magnetic fields can interact with each other, and that's kind of where we need to start. So in 1820, this character by the name of Hans Christian Ørsted, while doing a lecture, discovered that a compass needle, so remember a compass needle is just a tiny magnet, would be deflected when it was brought near a current-carrying wire. So this is a very important observation. So here's kind of how the experiment worked. He took a wire, I'm going to kind of draw it going into the page, three-dimensional drawing, I know, and the compass, when you lay it next to that wire, still points to the north. But when you take that same wire and you run a current through it, the compass needle gets deflected in some other direction. In other words, it doesn't point towards the north anymore. And so what's happening here is that the current in the wire, remember current is just a moving charge, creates a magnetic field that interacts with the Earth's magnetic field, makes the compass point a different direction. So the big idea that Ørsted discovered is that currents will create a magnetic field. So let's talk a little bit more about this magnetic field. Upon further experimentation, Mr. Ørsted discovered that the compass would always point at a right angle to the wire. So because this is kind of hard to draw in 3 dimensions, I'm going to kind of draw the current in the wire like this. So you can imagine there's a wire going into the screen. So like you're looking at it from behind, and the current is going into the screen. So I can represent an arrow moving into the page with an X, like that. And what he discovered was that a compass placed over here would point upwards. A compass put above the wire would point to the right. A compass that was placed to the right of the wire would point down, and a compass put below the wire would point to the left. And so basically what he discovered is that the magnetic field created by this current-carrying wire is a circular field around the wire. So it's like a circle. Concentric circles moving outwards. And we define the magnetic field from the compass. Basically, we just say that the direction of a magnetic field is the direction that a compass needle points. And so since the compass needle would point in a circle going around the wire, we say the magnetic field is a circle around the wire. So in order to determine which way the magnetic field would go, we use a real simple rule called the right-hand rule, which you can abbreviate RHR for short. So if we have a wire, this is how we would determine the direction of the magnetic field around the wire. And the way that it works is pretty simple. If you point your thumb in the direction of the current, make sure you're using your right hand, by the way. Point your thumb in the direction of the current, Then curl your fingers like you're grabbing a pole, not like you're making a fist. So your hand would look like that. Then your fingers indicate the direction of the magnetic field. So depending on the spot you're interested in, you can rotate your hand, keeping your thumb pointing in the direction of the current, and the tips of your fingers will be pointing in the direction of the magnetic field at that location. So for example, suppose we have a current going to the right. Well, if you point your thumb to the right, kind of like you're hitchhiking, and then curl your fingers like you're grabbing a pole, not like you're making a fist, and then keep your thumb pointed to the right, and then rotate your hand so that your fingers are in the direction or at the location that you're interested in. So let's say we wanted to know the magnetic field in the region below the wire. So if you keep your thumb pointed to the right, and then rotate your hand until it's below the wire, then your fingers should be pointing into the screen, or a piece of paper, if you're working on a piece of paper. And so underneath this wire, the magnetic field is into the screen. Now keep your thumb pointing to the right, and then rotate your hand backwards, so pull it back so that now your fingers are on the top side of the wire, and your fingers should have rotated so that they are pointing out of the screen. And so above the wire, we have a magnetic field pointing out of the screen, which should make sense if one side is going in, the other side should be coming out, so that they would make concentric circles. So let's look at another example. Here we have a current coming out of the page, so that could be indicated by a dot. Imagine an arrow coming towards you, you would just see a dot. And see if you can determine what the magnetic field, or the direction of the magnetic field would be at each of those dots real quick. Over on the left side, I got it to be pointing down. So if your thumb's pointing out of the screen, and then you rotate your fingers to the left, then your fingers would be pointing downward. And if you kind of pull your fingers back, so now they're on the right side, they would be pointing upwards. If your fingers are above the wire, they should be pointing to the left, and below the wire, they should be pointing to the right. So it's real important to remember that the magnetic field around a wire is circular. That'll help us fill in some of those gaps. So let's talk about the size of the magnetic field. How big can this magnetic field be? First of all, we need a symbol for the magnetic field. For some reason, I'm not really sure why this is, we use the symbol capital B for the magnetic field. And since it is a vector, it's very important we put that vector arrow over it. The unit that we measure the magnetic field in is the Tesla, named after Nikola Tesla, who invented a lot of things that involve electricity and magnetism working together. We'll talk about some of those things as we go. The magnetic field depends on three things. One is the size of the current. The more current there is, the bigger the magnetic field will be. The second thing is the distance from the wire. We give that the symbol R. It's a spherical relationship, really, so it's really a radius. And then the third thing is just the nature of space itself. We need a constant to take into account how space is constructed. And that constant is referred to as the permeability of free space, or the vacuum permeability. And it's given the symbol mu subscript 0, or mu naught. Mu naught has the value of 4 pi times 10 to the negative 7 Tesla times meter per ampere. That's not something you need to memorize. It's on your formula chart. You just need to be able to look it up when you need it. So putting all those things together, the constants in our equation is going to be mu naught over 2 pi, and so you'll see that the pi's would cancel out, and then I over R. The bigger the current, the bigger the field. the farther away you are from the wire, the smaller the field, which should kind of make sense. And then the stuff in front of it, all this business right here, is just a constant. So, for example, what is a magnetic field? 10 centimeters from a wire, which is carrying a 10 ampere current. So you're pretty close to a wire with a very big current. So just using our equation, mu naught I over 2 pi r, substituting in, that comes from our formula chart when we need it. Current is 10 amps, 2 pi is a constant, and then make sure you convert the centimeters to meters. Notice that the pi's cancel out. That's why we write mu naught in terms of pi. It's going to cancel out with that pi. And we would get something like 2 times 10 to the 5th. And then notice that the amperes and the meters cancel out, leaving us with just Tesla. And so we get something like 2 times 10 to the negative 5th Tesla. A Tesla is a pretty big unit for a magnetic field. The vast majority of the magnetic fields that we'll be dealing with won't be any bigger than that. So 2 times 10 to the negative 5th Tesla is a pretty typical size magnetic field for us. Let's look at another example real quick. Suppose that we had 2 wires, and we're going to pick a point which is right in between them, so 10 centimeters from both. And let's say one wire's got a 10 amp current going into the screen, and the second wire's got an 8 amp current coming out of the screen. And we want to know what's the magnetic field at point P, which is right in between them and 10 centimeters from both. So if we use our right-hand rule for the first wire, which I'm going to call wire 1, if we point our fingers into the screen and then curl them around to point P, our fingers should be pointing downward. And so I'm just going to start a vector diagram. I'm going to draw an arrow going down. If we do the same thing for wire 2, now we point our fingers out of the screen and then curl them around to point P, we would again have them pointing downward. So these magnetic fields are both pointing in the same direction, they're both pointing downward. And so it's important to remember that the magnetic field is a vector. We can treat it just like any other vector. And so the net magnetic field will be the sum of the two, the sum because they're in the same direction. And so I just got to find the magnetic field due to both of them and add them up. And so you can factor out some of those terms, like the mu naught over 2 pi. And you can also factor out the r, since they're equidistant from each other. They have the same radius. And then it would just be the currents left over that would be different. And so substituting would give you something like that. And so we'd get something like 3.6 times 10 to the negative 5th Tesla. And then it's important to remember to indicate the direction. That would be downward. So it's important to remember that all of our vector operations apply to all fields. And so we can deal with multiple fields if we need to, just do a vector diagram. Okay, let's talk a little bit about permanent magnets and bar magnets, which you might be more familiar with. And not all of this is really necessary to write down, so I'll kind of make sure we highlight the stuff that's important here. We're going to define a term called the magnetic moment. And the magnetic moment is the intrinsic property, so property means it's something it has because of what it is, of an electron. Remember, electrons are the negative charges that move around an atom, which basically causes them to act as a tiny magnet. At some point in chemistry, you probably learned about the quantum numbers, like your 1s1, 2s2, all that good stuff. And then the last quantum number is the spin quantum number. And the spin quantum number could have one of two values, either plus a half or minus a half. What you're probably more familiar with is representing them as an arrow spinning up or down. And so when you did electron configurations, the last thing you did was drew arrows either pointing up or down to represent the electrons. And those up and down arrows represent the direction of the spin, which determines the direction of the magnetic field created by an electron. Most of the time, the vast majority of the time, all these magnetic fields will end up canceling out. And so there's two types of properties which create, or two types of atoms rather, materials, which create weak magnetic effects. Diamagnetic materials contain paired electrons, and they are weakly repelled by a magnetic field. For example, helium, being a noble gas, would have 2 electrons, and so helium would be diamagnetic. If you try to put helium in a magnetic field, it would be very weakly repelled by it. A paramagnetic substance is something that contains unpaired electrons and are weakly attracted into a magnetic field. An example of that would be boron. Boron has 5 electrons, and so if you do the electron configuration for boron, it would look like that. And so there would be 1 unpaired electron, so boron would be paramagnetic. Now the important materials we need to know about are ferromagnetic materials. These are materials which for some reason, it's really hard to understand, and so we're not going to try, where adjacent atoms can interact somehow so that the electrons have a magnetic field or spin that are the same direction. Basically, the atoms will cooperate with each other and arrange themselves into a clump, which is called a magnetic domain. So domain is the really, really important key thing here. We need to be able to draw what the domains look like in a ferromagnetic material. So again, materials that do this are called ferromagnetic. And there's 3 elements which are ferromagnetic. Those are iron, cobalt, and nickel. If you were to look on a periodic table, you would see that those 3 are basically right next to each other. And so just due to their size of their atoms and the properties of their electrons, they exhibit this behavior. And so if you look at a common material, most materials, the electrons would be creating magnetic fields that are basically pointing at random. And so they kind of cancel each other out. In a ferromagnetic field, those electrons are all creating magnetic fields which point in the same direction. And so they kind of line up like this. And when they all line up, we refer to that as a magnetic domain. Now it's important to understand that even though the atoms nearby will line up their magnetic fields with each other, the domains throughout the entire sample of that object, in this case iron, do not necessarily line up. So I kind of drew some gray lines sketching out the magnetic domains, and then I'm drawing an arrow indicating the magnetic moment of that domain. So the direction that the electron's magnetic field is pointing. And so most of the time they just all point at random still. And so a piece of iron is no more magnetic than a piece of copper in most situations. Now what is going to change, so there's no order between the domains, but what is going to change that is when you place it in a magnetic field. So if we were to take that piece of iron and we were to put it in a magnetic field going to the right, those magnetic domains would line up with the magnetic field. And so if you put a piece of iron in a magnetic field, you get a bigger magnetic field because the magnetic domains of the iron will line up with the magnetic field. Basically, they reinforce it. So what's happened is you've created a magnet. Now, for the most part, this effect is going to be temporary. So like as soon as you turn off the magnetic field or remove the iron from it, it'll go away, unless the field is very strong. So if you have a very strong field, and that's again a relative term, then you can make a permanent magnet from your ferromagnetic material. And so that's how magnets are created. You basically put them inside a very large magnetic field, piece of iron that is, and then the field becomes so strong that the effect becomes permanent. Other materials besides iron, like alloys of neodymium, for example, can create really strong permanent magnets from medium strong magnetic fields. Real quick, the idea of a magnetic pole, if you have a solid magnet, like a piece of iron, then it's said to have poles, which are named north and south, which kind of look like that. Every magnet has to have both a north pole and a south pole. You never see an isolated pole or a monopole in nature. Remember, electrons themselves act like tiny magnets. It's those electrons which give things that magnetic property. So if you were to take a magnet and you were to break it in half, kind of like this, basically what you end up with is just two magnets. It's probably not going to be as strong as the original magnet, but now you've got two magnets. You're going to get a new south pole and a new north pole, so that both pieces have a north and a south pole. Last thing, the field around a magnet is going to be like a loop, kind of like that, and the field lines are always going to point from north to south. Remember that the field lines indicate the direction that a compass points. So, if you've ever used a compass before, you would know that a compass points towards the quote-unquote North Pole. I'm going to say the Arctic, just so that we don't get ourselves confused. And so if you imagine as the Earth having like a little bar magnet inside of it, more like a giant bar magnet, if a compass needle is pointing towards the Arctic, then the Arctic must be a south pole. Of that permanent magnet. And so the actual name for the North Pole of the Earth is actually the north-seeking pole. It seeks the north end of the compass magnet. And so as far as magnetic fields go, the North Pole of the Earth is really a south magnetic pole. Something that's kind of important to understand. And in class, we'll talk about the importance of the Earth's magnetic field and why we really can't live without it. So I think that's enough magnetic fields for today. Sorry that this was kind of long. There's a lot of information. The important things we need to be able to do is figure out the direction of a field, figure out how big it is, and explain how you can create a magnet from something like a piece of iron. And so we'll do some things in class. Hopefully they'll help us understand. Until then, ta-ta.